To determine the service size when there is no main breaker or disconnect outside, measuring the thickness or cross-sectional area of the incoming wires will work. Wires are generally sized using American wire gauge numbers, with larger numbers indicating smaller wire sizes. Refer to an American wire gauge thickness table or use a wire gauge measuring tool to determine the wire size based on its thickness in inches or mils. If there is any insulation left in the wires, look for markings indicating the wire size, such as number 6 or 6 American wire gauge. Using a special probe, you can pierce the cable insulation and measure the thickness of the copper conductor inside. If you have access to samples of known wire sizes, you can visually compare the thickness of the unknown wires to determine their size. Number 4 American wire gauge wire can handle 125 amps and number 6 American wire gauge wire can handle 90 amps. If the incoming wires are number 4 American wire gauge or larger, the service is likely already sized for 150 amps. The meter can ammeter used for a 100 amp service may not be sufficient for a 150 amp service. Check the manufacturer's specifications to ensure they are rated for the increased current load. If the service is already sized for 150 amps, a panel change can be performed without needing to upgrade the wires or other components. This will save time and money. Remember that electrical work can be dangerous, and you may want to consult a licensed electrician. When determining the appropriate size of electrical service for a building, several factors must be considered to ensure safety and compliance with the National Electrical Code, also known as the NEC. These factors include the total load calculation, demand factors, conductor ampacity, and overcurrent protection. The first step is to calculate the total connected load of the building. This involves identifying all electrical loads, such as lighting, receptacles, appliances, heating, ventilation, and air conditioning equipment, and summing their individual power requirements in volt amps or watts. For lighting, include the wattage of all installed fixtures. For receptacles, assume a minimum load of 180 volt amps per outlet in non-dwelling units and follow NEC guidelines for dwelling units. For appliances and equipment, use the nameplate ratings. After determining the total connected load, apply demand factors to account for the fact that not all loads will operate simultaneously at their maximum rating. Demand factors are percentages that reduce the total connected load to a more realistic estimate of the actual load. The National Electrical Code provides tables with demand factors for various types of occupancies and loads. For example, NEC Table 220.42 provides demand factors for general lighting loads in dwelling units, while NEC Table 220.84 offers optional calculation methods for dwelling units. Demand factors vary depending on the type of occupancy and the number and size of the loads. Apply the appropriate demand factors to the different load categories and sum the results to obtain the maximum demand load. The maximum demand load represents the maximum amount of power the electrical service is expected to supply at any given time. Once the maximum demand load is determined, calculate the required ampacity of the service conductors. Ampacity refers to the current carrying capacity of a conductor, measured in amps. To calculate the required ampacity, divide the maximum demand load in volt amps by the system voltage. For example, if the maximum demand load is 30,000 volt amps and the system voltage is 240 volts, the required ampacity is 30,000 divided by 240, which equals 125 amps. Select service conductors with an ampacity equal to or greater than the calculated required ampacity. Refer to NEC Table 310.15 for the ampacity of various conductor types and sizes, considering the conductor's insulation type and the ambient temperature. Ensure that the selected conductors are suitable for the application and are properly installed and terminated. Choose an appropriate size for the service overcurrent protection device, typically a circuit breaker or fuses. The overcurrent protection device should have an ampacity rating that is equal to or greater than the calculated required ampacity of the service conductors, but not exceed the maximum allowable ampacity of the conductors. The National Electrical Code provides rules for sizing overcurrent protection devices in Section 240.4. Ensure that the overcurrent protection device is properly coordinated with the service conductors and other components of the electrical system to provide adequate protection against overloads and short circuits. In addition to the above steps, consider any future expansion plans or potential increases in electrical load. It is generally advisable to oversize the service to accommodate future needs, especially in commercial or industrial buildings where load requirements may change over time. Consult with a qualified electrical engineer or contractor to perform a comprehensive load calculation and determine the appropriate size of electrical service for the specific application. They can assess the existing electrical system, evaluate the building's electrical needs, and ensure compliance with all applicable codes and regulations. Also, the existing meter enclosure must also be checked to ensure that it is rated for the appropriate amperage that is being installed. Lastly, local utility companies usually have guidelines and requirements as well when determining the maximum amperage that is being pulled from the line. When upgrading an electrical service, several potential issues and considerations can arise. Firstly, the existing electrical panel may need to be replaced to accommodate the increased amperage. The new panel must have sufficient breaker slots to handle all existing and future circuits. Additionally, the panel's short circuit current rating, also known as the SCCR, must be adequate for the available fault current at the service entrance. A qualified electrician should perform a fault current study to determine the available fault current and ensure that the panel's SCCR is sufficient. Secondly, the service entrance conductors, which run from the utility company's transformer to the main service disconnect, may need to be replaced with larger conductors to handle the increased amperage. The size of the service entrance conductors must be calculated based on the calculated load and the allowable ampacity of the conductors, as specified in the National Electrical Code. Ensure that the new conductors are properly sized and installed to prevent overheating and voltage drop. Thirdly, the grounding and bonding system may need to be upgraded to comply with current electrical codes. Proper grounding and bonding are essential for safety and to prevent electrical shock hazards. The grounding electrode conductor, which connects the grounding electrode to the service equipment, must be sized according to the size of the service entrance conductors. Additionally, all metal parts of the electrical system, such as conduit, enclosures, and equipment, must be properly bonded together to create a low impedance path for fault current. Fourthly, the existing meter enclosure may need to be replaced with a larger enclosure to accommodate the new meter and service entrance conductors. The meter enclosure must be rated for the increased amperage and must comply with the utility company's requirements. Coordinate with the utility company to ensure that the new meter enclosure meets the specifications and is properly installed. Fifthly, any existing subpanels or branch circuits may need to be upgraded to handle the increased load. Evaluate the capacity of each subpanel and branch circuit to ensure that they are not overloaded. If necessary, replace existing circuit breakers with higher amperage breakers or install additional circuits to distribute the load. Sixthly, consider the location of the new service equipment and ensure that it meets all applicable clearance requirements. The National Electrical Code specifies minimum clearances for electrical equipment to ensure safe access and prevent obstruction of ventilation. Verify that the new service equipment is installed in a location that meets these clearance requirements. Seventhly, obtain all necessary permits and approvals from the local electrical inspection authority before starting any work. Electrical work is typically subject to an inspection to ensure compliance with electrical codes and regulations. Coordinate with the electrical inspector to schedule inspections at various stages of the project and address any deficiencies promptly. Eighthly, document all changes and upgrades to the electrical system, including updated panel schedules, wiring diagrams, and equipment specifications. Accurate documentation is essential for future maintenance and troubleshooting. Keep a record of all permits, inspections, and approvals for future reference. Ninthly, consider energy efficiency when upgrading the electrical service. Install energy-efficient lighting, appliances, and equipment to reduce energy consumption and lower utility bills. Use smart home technology to automate lighting and appliance control and optimize energy usage. Tenthly, perform a thorough inspection of the entire electrical system after the upgrade is complete to ensure that everything is functioning properly. Check all connections for tightness and proper insulation. Test all circuit breakers and ground fault circuit interrupters, also known as GFCIs, to verify their functionality. Address any issues promptly to prevent electrical hazards and ensure the long-term reliability of the electrical system. When dealing with electrical systems, it's important to remember several key safety considerations. Electricity poses significant risks if not handled properly. Before starting any electrical work, always turn off the power at the main service disconnect. This will de-energize the circuits you'll be working on and reduce the risk of electric shock. Use a voltage tester to verify that the power is indeed off before touching any wires or components. Wear appropriate personal protective equipment, also known as PPE, including safety glasses, rubber gloves, and insulated tools. Safety glasses will protect your eyes from flying debris or sparks, while rubber gloves and insulated tools will provide insulation against electric shock. Never work on electrical systems in wet or damp conditions. Water is an excellent conductor of electricity, and working in wet conditions significantly increases the risk of electric shock. If you must work in damp environments, take extra precautions such as using ground fault circuit interrupters, also known as GFCIs, and wearing waterproof clothing. Inspect all tools and equipment for damage before use. Damaged tools can be hazardous and may increase the risk of electric shock or injury. Replace any damaged tools immediately. Never overload electrical circuits. Overloading circuits can cause overheating, which may lead to fires. Know the amperage rating of your circuits and avoid plugging in too many devices at once. Use power strips with built-in circuit breakers to protect against overloads. Be aware of overhead power lines when working outdoors. Maintain a safe distance from overhead power lines to avoid accidental contact, which can be fatal. If you're working near power lines, contact the utility company to have them de-energized. Use caution when working with ladders near electrical equipment. Metal ladders can conduct electricity, so avoid using them near electrical panels or overhead power lines. Use fiberglass ladders instead, which are non-conductive. Never bypass safety devices such as fuses or circuit breakers. These devices are designed to protect against overloads and short circuits. Bypassing them can create a serious fire hazard. If a fuse or circuit breaker trips frequently, investigate the cause and correct the problem instead of simply replacing it with a higher rated device. Be aware of the location of all underground utilities before digging. Contact the local utility companies to have them mark the location of underground cables and pipes before you start digging. This will prevent accidental damage to underground utilities, which can be dangerous and costly. Store flammable materials away from electrical equipment. Flammable materials can easily ignite if exposed to sparks or heat from electrical equipment. Keep flammable materials in a safe location away from electrical panels, outlets, and wiring. Educate yourself about electrical safety and follow all applicable codes and regulations. Electrical codes and regulations are designed to protect people and property from electrical hazards. Take the time to learn about these codes and regulations and follow them carefully. If you are not comfortable working with electricity, hire a qualified electrician. Electrical work can be dangerous, and it's always best to hire a professional if you're not sure what you're doing. A qualified electrician will have the knowledge, skills, and experience to perform the work safely and correctly. Always use the correct size and type of wire for electrical connections. Using the wrong size or type of wire can create a fire hazard. Consult the National Electrical Code for guidance on selecting the appropriate wire for your application. Make sure all electrical connections are tight and secure. Loose connections can cause overheating and arcing, which may lead to fires. Use a torque wrench to tighten connections to the proper torque specification. Protect electrical cords from damage. Avoid running cords under rugs or furniture where they can be damaged. Do not nail or staple cords to walls or floors. Replace any damaged cords immediately. Use ground fault circuit interrupters, also known as GFCIs, in wet locations. Ground fault circuit interrupters, also known as GFCIs, are designed to protect against electric shock in wet locations such as bathrooms, kitchens, and outdoor areas. Install ground fault circuit interrupters, also known as GFCIs, in all wet locations and test them regularly to ensure they are functioning properly. Follow the manufacturer's instructions for installing and using electrical equipment. Read the manufacturer's instructions carefully before installing or using any electrical equipment. Follow the instructions closely to ensure safe and proper operation. Avoid using extension cords as a permanent wiring solution. Extension cords are intended for temporary use only. If you need a permanent wiring solution, have an electrician install additional outlets. Never modify electrical equipment without proper authorization. Modifying electrical equipment can create a safety hazard and may void the manufacturer's warranty. Consult a qualified electrician before making any modifications to electrical equipment. Keep electrical panels clear of obstructions. Electrical panels need to be easily accessible in case of an emergency. Keep the area around electrical panels clear of obstructions such as boxes, furniture, and equipment. Regularly inspect electrical systems for signs of damage or wear. Look for frayed wires, cracked outlets, and loose connections. Have any problems, repair it promptly by a qualified electrician. By following these safety guidelines, you can reduce the risk of electrical accidents and ensure a safe electrical environment. Always remember that electricity is a powerful force and should be treated with respect.